In this lecture, we're going to talk about how you can obtain the graphs of certain functions by applying transformations to a well-known function. In certain situations, all you have to do is take a graph that you're familiar with and maybe shift it, compress it, stretch it, reflect it, maybe some combination of those things, and obtain the graph of a more complicated function. We're going to start with the vertical shifts because they're probably the most intuitive. In this first rule, we're going to talk about a shift upward. Let c be greater than 0. The graph of y equals f of x plus c is obtained by shifting the graph of y equals f of x upward by c units. Compare the function we want to graph with the function that we're translating. You can see we've added c on the outside of the function that increases the output y by c units. So every y coordinate of the graph we want to get is c units bigger than the graph that we're starting with. So the graph's going to shift up by c units. Here's an example to demonstrate that. We're going to sketch the graph of f of x equals x squared plus 3. In each of these examples in the lecture, I'm always going to draw the base function, the library function that we're working on, and then apply each transformation one at a time. So we're going to have multiple graphs sketched on the same set of axes. The ultimate goal is to understand these rules well enough that you have a vague notion of what the graph will look like without having to draw each individual step. I don't think it's a good idea for me to do that here, so I'm always going to show all of my work. But eventually you want to know these cold enough so that if I draw a graph later in this class or a future instructor draws a graph, you'll know where they got it from even if they don't show all of the intermediate steps. So the base function that I know well, the library function I'm working off of, is y equals x squared. We know that that's a parabola that emanates from the origin. So I'm going to start by drawing that. And I'm going to label that so that you know that that's not my final graph, that's just the function that I'm starting with. Our rule says that because we're adding a positive number on the outside, we're going to shift the graph upward by that many units. In this example, we're adding positive 3, and so that's going to shift every point of this graph up 3 units. In particular, the point at the origin is going to shift from 0, 0 to 0, 3. You can see it. If you were to plug 0 into the function, you'd get 0 squared plus 3, which is 3. Every other point also translates up 3 units. And we do our best to draw a graph similar to the one before. We're not trying for perfection here. If we wanted perfection, we'd use technology. If we wanted a good graph by hand, we'd plot more than just one point. We'd plug a bunch of numbers in for our x, get all those y coordinates, and get a nice graph on graph paper. The point here is to get a sketch of the graph, just a vague notion of what the graph looks like. We have the right shape, it's supposed to be a parabola, it's opening in the correct direction, and we've translated the vertex to the correct spot. We have a pretty good idea of what this graph looks like. I've labeled this one as well so you can tell that it's my final answer. The graph of f of x equals x squared plus 3 is just the graph of y equals x squared shifted up 3 units. Every point gets translated 3 units up. There's a similar rule for when you subtract a number. We want c to be positive again here so that when we subtract, we don't have to worry about a minus negative situation. So let c be greater than 0. The graph of y equals f of x minus c is obtained by shifting the graph of y equals f of x downward by c units. The logic is the same. All of the y coordinates are getting reduced by a value of c, and that's going to shift the graph down c units. Our example here is to sketch the graph of g of x equals the principal cube root of x minus 2. The cube root function is the library function that people are probably the least familiar with. It's the one that kind of snakes horizontally through the origin like this. That's y equals the cube root of x. We're going to take that graph and shift it down by 2 units because we're subtracting 2 on the outside of the function. We're reducing every output by 2. In particular, that point at 0, 0 is going to shift downward by 2 units. And then do your best to draw something parallel to the original graph, just 2 units lower. Now, is that graph perfect? No, but the point isn't perfection. The point is to have a basic idea of what's going on. I can see that this graph is supposed to go through 0, 2. I still have the basic shape. I can see that it's increasing over its entire domain. Those are the things that we're looking for. So there are the 2 rules for vertical shifts. Now let's look at the horizontal shifts, and a lot of people think that these rules are not intuitive. Here's our first rule. Let c be a positive number. The graph of y equals f of the binomial x minus c is obtained by shifting the graph of y equals f of x to the right by c units. So there's a notational part that I need to explain, and I need to explain how the shift is done, because for a lot of people it's counterintuitive. First, f of the quantity x minus c means that we're not adding and subtracting on the outside of our base function, but rather directly from the input. Here's an example just to show you what I mean. Here we're asked to sketch the graph of y equals the square root of the binomial x minus 5. Notice that the minus 5 isn't outside of the function like it was in our cube root example. It's actually underneath the radical. The 5 is being subtracted directly from the input. This indicates that it's some sort of horizontal effect. Here's the other weird part. When we subtract c from the input, for a lot of people, their expectation is that that would shift the graph to the left, but it actually shifts the graph to the right, and we'll be sure to explain why as we do this example. Here we're sketching the graph of y equals the square root of x minus 5. Notice that I didn't use the function notation here. It doesn't matter whether I call it f of x, g of x, or just y. You graph it the same way. We're going to start with our base function, which is y equals the square root of x. That one we're familiar with. That's that half parabola that opens kind of to the right, emanating from the point 0, 0. We're subtracting 5 directly from the input, and this rule claims that we want to shift the graph to the right. A common mistake is to shift this to the left because minus 5 seems like it would shift it to the left. But if I shifted the graph 5 units to the left, that would put a point at negative 5, 0. Plug negative 5 into that function and tell me what you get. Right, you don't get a real number at all. That point wouldn't shift 5 units to the left. Plug in positive 5 for me and tell me what you get. Exactly, you get 0. That point at 0, 0 gets shifted over to the point 5, 0. That subtraction of 5 actually shifts that point 5 units to the right, not 5 units to the left. The graph should essentially have the same shape from there. I did not do a good job of labeling my base function. Let me do that, and of course I'm going to label my final answer. When you're doing practice problems for yourself, I would encourage you to label all of your pieces. But ultimately, it's the final graph you need to label because that's the one that we want. And by applying this transformation, we automatically know special things about this function, like we can see its domain. The domain of the function we actually wanted to graph is from 5 to infinity, including 5. The other horizontal shift should make sense if you now understand this one. Let c be some positive number. The graph of y equals f of x plus c is obtained by shifting the graph of y equals f of x to the left by c units. So we're adding c directly to the input, and that's going to shift the graph to the left. Let's sketch the graph of f of x equals x plus 6 quantity cubed, the cube of the binomial x plus 6. I like this example because if this thing was multiplied out, it would look like a nightmare to graph, when in fact it's pretty easy to do. We're going to start with our base function, which is y equals x cubed. That's that one that kind of snakes vertically through the origin like this. And now we're going to apply this translation. Looking back at the rule, because we're adding a positive number directly to the input, not on the outside of the function, but inside, directly on the x. That shifts the graph to the left 6 units. And again, just to make sure that makes sense why we would do that, if I want to get an output of 0 from our new function, I'd have to plug in negative 6. It's negative 6, comma 0 that sits on this graph. You can see that by just plugging in negative 6. If you plug in positive 6, you're going to get 12 cubed, which is 1,728. Thank goodness we don't have to plot that point. We're going to plot the point at negative 6, comma 0, shifting the base graph, our library function, 6 units to the left. And now we draw the same basic shape. I want you to notice that my graph does not look perfect. It doesn't even look like a direct translation of the red graph. That is not the point of this. Don't try to get it perfect. You want to have the right shape, and please don't go out of your way to make it look awful, right? Don't test the limits of what constitutes a good graph or a bad graph. Try to make it look similar, but also don't waste 10 minutes worrying about whether or not you got the curvature perfect. We have a pretty good idea that this is what the function would look like. And just to reiterate, what I really want you to be able to do is just see that if I were to graph it. So later on in a lecture, if we had this function and I just drew this graph immediately without explaining, you should know why the graph looks like that. You should know why I put it through -6, 0 and why it's shaped the way it is. That's really all I want. Being able to graph these things by hand is antiquated because we don't need to do that anymore. I just want you to have this knowledge of the translations. I don't actually care how good your graphs are. Now that we've seen horizontal and vertical shifts, let's do an example that incorporates both. Let's sketch the graph of f of x equals the absolute value of the sum of x and 3 minus 4. The base function here, the library function we're working off of, is the absolute value of x. That's that V-shaped graph that comes out of the origin. Now we need to apply the translations. There's a vertical and a horizontal. In this example, it does not matter what order we apply the transformations. When you shift horizontally and then shift vertically, you're going to get the same graph as when you shift vertically and shift horizontally. But once we've got our entire list of possible transformations, it will matter what order we do some of them in. Sometimes it matters what order you choose to do things in. And so my advice is to apply the transformations in the order of operations. If we were to plug a number in for x, the first thing we would do is add 3. So that's the first transformation I'm going to apply. Adding 3 directly to the input shifts the graph 3 units to the left. That's the last rule that we did. So I'm going to take that V shape and shift it 3 units to the left. In particular, I'm going to shift that vertex 3 units to the left. And then I'm going to try to draw the same V shape. This is just y equals the absolute value of x plus 3. That's not the final graph. All I've done is the horizontal shift. Then from that new blue graph, we're going to subtract 4. So we're going to shift this graph down 4 units. We're going to shift the blue graph because that's the one that we're subtracting 4 from, not the red graph. That blue graph gets shifted down 4 units. Down because we're subtracting. The vertical rules follow intuition better. When you subtract a number, it shifts it downward. And so I'm going to take that vertex at -3, 0 and shift it down to -3, 4 and draw that same V shape. This is the graph of f of x. The intermediate steps I'll always label completely, but for the final function I'm just going to label it with the name of the function. Let's move on from the shifts and talk about stretches and compressions. Our first rule will be for a vertical stretch. Notice the rule is a little bit different here. We're going to let c be some number greater than 1. The graph of y equals c times f of x is obtained by vertically stretching the graph of y equals f of x by a factor of c. Here we're multiplying on the outside of the function by a number bigger than 1. That's like multiplying all of the y coordinates by that number. So you're stretching the graph away from the x-axis. All of those y coordinates get stretched by a factor of c. We're essentially multiplying the distance from the x-axis by c. So any points that are on the x-axis will stay on the x-axis, and the points that aren't on the x-axis will get further away. How much further away? C times as far as they were before. You multiply by c. Here's an example. We're going to sketch the graph of f of x equals 4x cubed. We know what x cubed looks like. It's the one that snakes vertically through the origin. We're going to take that graph and stretch it vertically by a factor of 4. Every point is going to extend 4 times as far away from the x-axis as it currently sits. Any point on the x-axis stays because 0 times anything is 0. All of these other distances should get 4 times as far. Now I'm not going to measure this with a ruler and make sure it's 4 times as far. I'm just going to try to guess at it a little bit. There's the current distance for this point. I just want to quadruple that. So 4 times as much. So twice as tall, 3 times as tall, 4 times as tall would be about here. I'm going to do the same thing in the third quadrant. Here's this distance from the x-axis. I'm going to quadruple that. 2 times as far, 3 times as far, 4 times as far. That would be like here. It's going to have that same vertical snake, but it's going to be a lot steeper. So it comes in like that. There's f of x. It's taller, and as a consequence, it winds up being skinnier as well. If you look at that horizontally, it looks like we smashed it and made it skinnier. But we're describing the effect in terms of a vertical stretch. Vertically, this graph has been stretched. We've taken every point on that graph and stretched it so that it's 4 times as far away as it used to be. You get a vertical compression, or what's sometimes called a vertical shrink, when the number you multiply by is between 0 and 1. Now you'll notice that we've only focused on positive numbers. We'll talk about the effect of multiplying by a negative number before we're done. Here's the rule of c is between 0 and 1. The graph of y equals c times f of x is obtained by vertically compressing the graph of y equals f of x by a factor of 1 over c. I think it's pretty clear why the graph gets compressed. We're multiplying all of the y coordinates by something between 0 and 1. So you're getting a fraction of what we had before. The way that we describe that might be a little confusing. We're saying we're compressing the graph by a factor of 1 over c, but let me explain. In this example, we're multiplying by 1/2. So we're going to compress the graph. We're going to squash it down. It's going to be 2 times closer to the axis than it was before. We're compressing it by a factor of 2. That's why we say it like that. It's all a matter of how you describe it. It's half as far, it's twice as close. So when we talk about what factor we're compressing it by a factor of 2. Don't get too hung up on that. You're just multiplying each distance from the x-axis by c. So in this example, we'd be multiplying all of these by 1/2. The cube root of x is the one that snakes horizontally through the origin. It looks like this. That's the cube root of x. We want to multiply all of those y coordinates by 1/2. We want to get it twice as close to the axis as it was before. Any point on the axis will stay on the axis. All these other points, the distance is going to be half as much as it is right now. So I'm just going to draw a couple of reference points here. That appears to be about halfway. Maybe that's a little high. I don't care. The point isn't to be perfect. That one's pretty good. That one actually looks like it's halfway between. And then I draw the same basic shape. Still snaking through the origin. It's just a little bit closer. Well, it's twice as close, half as far. This blue one is our f of x. All right, let's mix this all together. Let's sketch the graph of f of x equals 3 times the square of the binomial x minus 2 plus 7. We've got 3 transformations here. I'm going to wind up with 4 parabolas in my picture. If it really bothers you, maybe draw all the graphs except the very last one on one set of axes and put your final answer on a second set of axes. So the library function we're basing it on here is the squaring function, y equals x squared. We know that's a parabola that emanates from the origin. It looks like this. This is an example where it would matter what order we did things in if you're describing it. I think a lot of you would do it correctly whether or not you perform these transformations in the correct order. But when you describe it verbally, it really matters which way you do it. According to the order of operations, first I should apply the minus 2. Think about what that should do to the graph, and if you're confident, draw yours in there. That minus 2 will shift the graph 2 units to the right. Every point shifts 2 units to the right. When you subtract directly from the variable, that's a horizontal effect, and they work counterintuitively. I'd have to plug in 2 in order to get a result of 0. So I'm translating this point at 0, 0 over to 2, 0. I once again forgot to label my base function. This is y equals x squared. And now I'll be sure to label this one. This is y equals x minus 2 squared. Technically, we apply the 3 next. And here's the reason why. If you shift the graph up 7 units first, and then say you're multiplying by 3, that's going to shift the vertex of this graph up to 21. But that's not right. This graph doesn't get shifted vertically until its very last step. So when you describe verbally that you're going to shift the graph up 7 units and then multiply all those y coordinates by 3, that doesn't give you the right point. The correct thing to do is to apply this vertical stretch first. Every point on the blue graph is going to get 3 times as far away from the x-axis as it currently sits. That's going to make this graph taller and skinnier. How much taller? Well, 3 times taller. So just measure a couple of spots here, like here, here. The point on the axis will not move. And we draw this green one. Taller and skinnier. That's y equals 3 times x minus 2 squared. And now we take that green graph and we shift it up 7 units. 1, 2, 3, 4, 5, 6, 7. Let's see, I'm running out of colors here. Let's try orange. I get this green graph shifted up 7 units, but still tall, skinny parabola, and there's my f of x. Here's what it would look like if I didn't have all the intermediate graphs in there, and I hope you can see where that graph is coming from. Think about it. We're taking the base parabola y equals x squared, we're going to shift it 2 units to the right, we're going to stretch it vertically by a factor of 3, making it taller and skinnier than usual, and then we're going to shift that skinny parabola up 7 units. We're going to wind up with a parabola that opens upward with a vertex at the point 2,7, and it's taller and skinnier than usual. That's what you need to be able to do. Okay, let's go on to horizontal compressions and stretches. We're going to start with the case where c is greater than 1. And again, for a lot of people, the rule is going to seem counterintuitive. The graph of y equals f of c times x, notice that the c is directly affecting the x. Just like in the horizontal translations, when we shifted left and right, the c was either added or subtracted directly to or from the x. Now the c is directly on the x again. This is going to be a horizontal effect. That graph is obtained by horizontally compressing the graph of y equals f of x by a factor of c. We're multiplying by a number bigger than 1, but it actually squashes the graph horizontally, opposite of what the vertical effect is. Here's an example of that. We're going to sketch the graph of y equals the absolute value of the product 5x. So we know what the absolute value of x looks like. It's that V shape that comes out of the origin. The 5 is multiplied on the inside. According to our rule, that's supposed to be some sort of compression. It's supposed to squash the graph. You compress it by a factor of c, so it'll be 5 times closer than it was before, which means you're multiplying by 1/5. So all of the x-coordinates have been reduced by a factor of 5. All of the x-coordinates have been multiplied by 1/5. Does that make sense? Well, let me pick a point. Like there's a point right here at 1, 1. Suppose I wanted to plug in a positive number and get an output of 1 from this function. What would I have to plug in? Not 5. I'm not going to stretch it 5 times as far away on the right side. I need to plug in 1/5. That point's going to be here. Same thing on the other side. That point's going to get squashed closer to the axis. The point on the y-axis doesn't move. And we get this graph. This is y equals the absolute value of 5x. I have to write the entire thing this time because I didn't give it a function name. I have another way to explain why this should make sense. We can actually algebraically take this expression and rewrite it. Y equals the absolute value of 5x can actually be rewritten as 5 times the absolute value of x because the absolute value of 5 is 5. From that perspective, that's a vertical stretch. And I hope you can see that that blue graph is a vertical stretch. That vertical stretch corresponds to a horizontal compression. Now for this example, those factors are the same. It got 5 times taller and it also gets 5 times skinnier. But that's not always true. It depends on what the function is. So when you multiply on the inside, directly on the x, by a number bigger than 1, that's going to horizontally compress the graph. It's going to get c times closer to the graph. You're multiplying the distance from the y-axis by 1 over c. So if you multiply by a number between 0 and 1, that's going to stretch the graph horizontally. The graph of y equals f of c times x is obtained by horizontally stretching the graph of y equals f of x by a factor of 1 over c. You're going to multiply the distance from the y-axis by 1 over c. c is between 0 and 1, so to stretch it, you're going to have to multiply by the reciprocal. For example, if you've got the square root of 1/3 x, that's going to stretch the graph not by 1/3. That doesn't even make sense to say. You can't stretch it by 1/3. You're stretching it by a factor of 3, which is the reciprocal of the number that we see. So y equals the square root of x is our base function here, our library function. It's that half parabola that kind of opens to the right. This is y equals the square root of x. I want to graph y equals the square root of 1/3 x. So we're going to stretch every point away from the y-axis by a factor of 3. Any point on the y-axis wouldn't move. You can see it. If you plug 0 in for x, you still get 0. All these other points are going to stretch 3 times as far away. So this point, I'll just stretch it that far. And this point maybe here. Now you'll notice it doesn't look 3 times shorter. It's been vertically compressed, but not by a factor of 3, and that's because when we do the algebra, we can actually rewrite this as the square root of 1/3 times the square root of x. And the square root of 1/3 isn't going to be 1/3. In fact, the square root of 1/3 is bigger than 1/3. And so the graph doesn't get vertically compressed as much as it gets horizontally stretched. That's bonus stuff that I can't help but explain. You don't need to be able to do that stuff, but I do want you to see that there is a connection between the horizontal stretches and the vertical compressions. And I feel like I have to explain why it doesn't compress as much as it stretches. Maybe you don't care, but I suspect there's a lot of things that I talk about that you don't care about, so I'm just going to keep rambling. So we've covered all of the multiplication by positive numbers, but what do you do when you multiply by a negative number? Well, that's going to be some sort of reflection. The graph of y equals the opposite of f of x, multiplying by -1 on the outside, is obtained by reflecting the graph of y equals f of x through the x-axis. So you're going to flip the graph vertically. All of the points above the x-axis are going to go below the x-axis, and all of the points that were below the x-axis will go above. So if we want to sketch the graph of f of x equals the opposite of the absolute value of x, I'm going to start with my base function, which is the absolute value of x. It's that v that comes out of the origin. And now our rule says that we're going to flip the graph vertically, and I hope you can see why. The absolute value function here is going to output a positive number, but then this negation is going to say, no, no, no. Now make all of those y coordinates negative. You're going to flip all of those to negative numbers. So the point on the axis stays at 0 because -1 times 0 is still 0. But all of these other points get flipped downward. If you're writing in a single color in your notes, it's going to look like you just X'd out this graph, so you might want to do something to make that stand out. This blue graph, that's f of x. It's been flipped vertically. Let me get rid of the other graph so you can just see it without being distracted. That's the graph of f of x equals the opposite of the absolute value of x. Once again, I want you to notice that that effect was on the outside of the function. If the negative is inside, directly on the x, then as you might guess, that's a horizontal effect. So this is going to be a horizontal reflection. The graph of y equals f of the opposite of x is obtained by reflecting the graph of y equals f of x through the y-axis. So that's a horizontal flip. Things on the left side of the y-axis will move to the right, and things on the right side will move to the left. Here's an example. Sketch the graph of y equals the square root of the opposite of x. Well, we know what y equals the square root of x looks like. It's that half parabola turned on its side. We're going to flip that horizontally. You can see it. You can't plug positive numbers in for x here because you'll wind up with negative numbers under the radical, which we can't have if we're trying to draw the graph. In order to get positive numbers under the radical, we're going to have to plug negative numbers in for x. So all of these points are going to get reflected in the opposite direction like this. Mirror image of the original graph where the mirror is on the y-axis. Again, this does more than just give us the graph. Drawing the graphs by hand is kind of silly in this day and age. But I immediately see, for instance, the domain of this function. The domain of this function goes from -infinity to 0, including 0. I can see that this new function is a decreasing function, not an increasing function like the other ones. And again, I just want you to be at a point where if I draw this graph later on in the course, you don't have to wonder where it came from. If I needed to graph this function, I would put no explanation for where it came from. I would just graph it. I'd like to think that I'm nice enough that if somebody asked, I would explain it. But in the back of my mind, I'd be like, damn it, shouldn't you already know this? Like, we already talked about this. Does that make me a bad person? Probably. But I can't help it. You should already know. And I mean you should already know how to graph this thing. I don't know if you should know whether or not I'm a bad person. You probably suspect it because I chose to teach math as a profession. I think most of us are kind of jerks. Okay, let's do a humdinger where we just put all this together. Sketch the graph of f of x equals -2 times the square of x plus 1 plus 3. I see 4 different transformations here. We've got a horizontal effect here where we're adding 1 directly to the variable. We've got a 2 multiplied on the outside, and we've got a negative multiplied on the outside. Those are 2 vertical effects, and then adding the 3 is also a vertical effect. I want you to try to picture where this graph is going to wind up without drawing any of the intermediate graphs. I'm going to draw all of them on the screen here, but before I do that, pause the video and see if you can determine what this graph is basically going to look like. See if you can visualize where it would be increasing and where it would be decreasing. See if you can determine its range. You can determine the range of the function just by thinking of those transformations. Try to come up with all of that information in your mind. Then unpause the video and see if you got it right. Okay, we're starting with good old y equals x squared, that parabola that emanates from the origin. The plus 1 is going to shift that graph 1 unit to the left. This blue one is x plus 1 squared. Next by the order of operations would be the 2 and then the negative. You could actually apply either of those. It doesn't matter which one you do first. The 2 is going to make it taller and skinnier. It's a vertical stretch by a factor of 2. I missed the x-axis there. I just cheated and made that point bigger. The negative is a vertical reflection. I know it's vertical because it's on the outside of the function. It's a reflection because it's multiplication by a negative. So I'm going to take that green skinny graph and flip it over the x-axis, vertical reflection, and then to that orange graph I need to add 3, which shifts the graph up 3 units. I think I'm going to switch back to black just because I've run out of choices here. So I'm going to take that orange graph and shift it up 3 units. That's my f of x. I know that's a nice, you can still see everything because I've used multiple colors, but it's pretty bad. So let me erase all of the extra junk so you can see the final answer. Is this basically what you pictured? A parabola that opens downward with a vertex at -1, 3? If so, you did a good job. You can tell where this function is increasing and decreasing. You can see that it's got a maximum output at 3, so you know what its range is. You can't really tell that I applied the vertical stretch because you have no frame of reference what my original graph looked like. If I were to draw this graph with no explanation, it would be hard to tell that I had applied the vertical stretch part. If I wanted to make sure I got that part right, I could find the x-intercepts. Set this thing equal to 0 just to get it better. That's not the point right now. We're just sketching graphs. So we're going to put this all together with a few more examples, but we're going to stop graphing and we're just going to explain everything in words. I like these questions because this is really what I want you to be able to do. I want you to be able to think about what the effects are. I don't want you to have to actually graph it, because if you need a graph, you don't do this by hand anymore. You use technology. This first one says, explain how to obtain the graph of y equals 3 times f of the opposite of x from the graph of y equals f of x. We're going to explain these steps in the order that you would apply them in the order of operations. Sometimes that won't matter, sometimes it does. To play it safe, just follow the order of operations. So in the order of operations, the first effect would be this negation on the x. On the inside of the parentheses, directly on the x, those are horizontal effects. And when you multiply by a -1, that's a reflection. So this is a horizontal reflection, or a reflection over the y-axis. So first, we should say the graph of y equals f of x, but we're just going to say reflect f of x. It's understood that we're reflecting the graph. So I'm abusing the language a little bit here. I'm not saying this perfectly, but I don't need you to say it perfectly. I know what you mean when you say reflect f of x. Well, I almost know. You have to tell me where you're reflecting it. Reflecting it over what axis? Well, here we reflect f of x over the y-axis because it's a horizontal reflection. You need to be careful about just saying reflect it horizontally, because you could reflect it horizontally over the line x equals 3. But that's not where we want to reflect it. We want to reflect it directly over the line x equals 0, the y-axis. After that reflection, we have to apply the 3. That 3 is on the outside, so it's a vertical effect. The vertical effects tend to follow intuition, so multiplying by 3 is going to be a vertical stretch. So then stretch, not f of x. That's not correct. We're not stretching f of x. We're stretching the graph that we came up with in the previous graph. So we're just going to say then stretch that graph. A little vague, but I know what you mean. The graph that we just came up with vertically by a factor of 3. Or you could say stretch all of the y-coordinates of that graph 3 times as far away from the x-axis. It's not really right to say stretch it by 3 units. Some of the points move more than 3 units away from the axis. They get 3 times as far away. So we're stretching it by a factor of 3. Let's do a couple more of these verbal ones. Explain how to obtain the graph of y equals the opposite of f of x plus 7 plus 10 from the graph of y equals f of x. The way I said that was a little ambiguous. The x plus 7 is inside the parentheses, the 10 is on the outside of the parentheses. Here, the order in which you explain this absolutely matters. In the previous example, it didn't matter. If you stretched it vertically and then reflected it, or reflected it and then stretched it, it wouldn't make a difference. Here, it absolutely matters what order you do these things in. We're going to follow the order of operations. The order of operations would tell us to start inside these parentheses. That's going to be a horizontal effect. When you add directly to the x, that shifts the graph to the left, not to the right. So first, shift the graph of y equals f of x. We're just going to say f of x. To the left, 7 units. That's probably not the best way to say that grammatically. Shift f of x 7 units to the left is probably the better way to say that. Too lazy to fix it. Next, let's see, what would be next in the order of operations? This multiplication comes before this, and it matters what order you do this in. Next, we're going to apply this negative on the outside. That's a vertical reflection. So we're going to reflect that previous graph over the x-axis because it's a vertical reflection. Then we apply the plus 10. That's on the outside, so it's a vertical effect, and it's going to shift the graph up 10 units. Writing that graph twice in a row is vague. It's not the best writing, except I'm imagining it with emphasis. So let me read it. First, shift f of x to the left 7 units. Next, reflect that graph over the x-axis. Then shift that graph up 10 units. Right? When you say it, put the emphasis in there. You can see why that graph would work. Honestly, I wouldn't care if you just took that part out. Take out all the references to the functions. That's a good explanation. It's understood what you mean. I'm not going to do it that way. Why does it matter what order we write these in? Let me show you with some pictures. For my demonstration here, I can't draw a graph because I don't even know what the function is. We don't know if it's a parabola or whatever. I'm just going to take one point and show you that it matters. I'm going to start with a point at 0, 0, and I'm going to apply all of these effects. First, I shift to the left 7 units. Okay, so that's going to wind up somewhere on the left. Then I reflect that graph over the x-axis. Okay, so that wouldn't move because it's already on the x-axis. Then I would shift that graph up 10 units. So that point would wind up above the axis, say here. Let me do the same thing, but in the wrong order. I'm going to start with a point at 0, 0. I'm going to shift that graph 7 units to the left, fine. Then I'm going to shift that graph up 10 units. Let me use an intermediate color like orange. Then for my final point, I reflect that over the x-axis and I wind up down here. That's not the same thing. The correct order was the way we did it first because of the order of operations. This is why the order you write these in matters. You don't wind up with the same point. We wind up with 2 different locations. One more. Why don't you try this one first? Explain how to obtain the graph of y equals 1/4 f of 2x from the graph of y equals f of x. Pause the video and write those out. It turns out in this example it doesn't matter what order you apply these in, but we're going to go with the order of operations here. First, we're going to start inside the parentheses. That's a horizontal effect. We're multiplying, so this is either going to be a stretch or a compression. What do you do when you multiply on the inside by a number bigger than 1? That's a compression. So first, horizontally compress the graph of y equals f of x by a factor of 2. Now we're multiplying by this 1/4 on the outside. Because it's on the outside, that's a vertical effect. When you multiply on the outside by a number between 0 and 1, that is a vertical compression. So we're going to vertically compress the graph by a factor of 4. It's going to be 1/4 as big as it was before. So we're compressing it by a factor of 4. So to get the new graph, we're going to take the original graph, squash it so that all the x-coordinates are twice as close to the y-axis, then squash that graph so that all of the y-coordinates are 4 times closer to the x-axis. That's the collection of transformations on graphs that I want you to be familiar with. You future trigonometry students should hit this pretty hard because you're going to need this in your class. For practice, I recommend that you spend more time writing out in words what you would do than actually drawing the graphs. If you're doing practice problems in a textbook that gives you the final graphs, I would recommend you just describe in words what you would do to the library function to get the final graph, and then just check the answer in the back of the book and see if that's what they did. Actually drawing the graphs probably isn't the best use of your time. What's important is to understand the transformations, not to be able to draw the graphs. A lot of information in this lecture, some of which doesn't follow intuition for some people. So if you have any questions for me, let me know. You can catch me in an office hour, shoot me an email.